Hi, and welcome to the Learn Electronics India channel. I am Meghna, and in this video, we will be learning about Introduction to Digital Electronics. We will understand the binary system, conversion of decimal to binary and vice versa. We will also learn about the logic gates and a basic introduction to digital circuits. Let us get started with the binary system. Binary means 2. Bi indicates 2, which means this entire system has only two digits, that is 0 and 1. So there are multiple systems, just like how we have the decimal system with digits 0 to 1. Like that we have hexadecimal, we have octal system, and we also have the binary system. So today we will be focusing on the binary system. Our entire computer communications, the programming languages which we use, the compiler compiles it, everything, every such communication happens in binary. So understanding the binary system is very important. It is the language in which machines communicate through. So we can also call it as the machine language. Let us now understand how to convert decimal to binary. So these are the steps involved. Now, if we consider this 0000, the right hand side, the rightmost digit, is the least significant bit. In decimal, we will consider this as units place. So in binary, it is called as the LSB or least significant bit. And the leftmost digit is called as the most significant bit or MSB. Let us understand by an example. So here I have 145 in decimal to be converted into binary. So first what I'll do is, since it is binary, binary has base 2. Decimal has base 10 because it has 10 digits, 0 to 9. Binary has 2 digits, 0 and 1, so it has base 2. So since I'm converting decimal to binary, I will divide the decimal number by 2, note down the quotient and the remainder. So first, after dividing 145 by 2, I will obviously get a remainder as 1 because 145 is an odd number. If the number is even, then I will get a remainder of 0. So like this, I will continue the process, and after dividing 2 divided by 2, quotient would be 1, remainder is 0. Now I will take this quotient again. 1 divided by 2, I got a quotient as 0. So until I get the quotient as 0, continue dividing the quotient by 2 and recording the remainders until the quotient becomes 0. Now my quotient has become 0 and my remainder is 1, which means this one digit is my MSB or the most significant bit, and the first remainder that I've obtained is the LSB. So the binary number or the 145 from decimal, when we convert it into binary, I will start writing from 1 and I will move upwards. So first I will start with MSB and then move towards LSB. This remainder itself I have written here. So 1 is my MSB, then 00 1 0 0. So 00 1 0 0 followed by a 1, which is the least significant bit. So this is how we convert a decimal to binary. We started by dividing by 2, noting down the quotient, noting down the remainder. That quotient again I will divide by 2, note down the quotient and remainder. Follow the steps until I get the quotient as 0. The binary number would be written by starting with MSB and then LSB, where MSB is the last remainder that I have obtained and LSB is the first remainder that I have obtained. For better understanding, you can try out these numbers and convert it into binary. Now let us do the vice versa, how we can convert binary to decimal. Again, binary has base 2. So first I will start by writing the binary number and count the powers of 2 from right to left, starting from 0. So I will write base 2, and for each base I will give a power. Now that power will depend on the position of that digit. For example, I have this number. I will start from my rightmost. So this digit, this I will give a position of 0. So the power would be 0, 2 to the power 0. Similarly, this would be 1. So I will give 2 power 1, then 2, 3, 4, 5, 6, 7. So the last one or the leftmost digit in this binary number will get a power of 7 or 2 to the power 7. Now next step is write each binary digit with corresponding powers of 2 from right to left such that MSB or the first binary digit will be multiplied by greatest power of 2. So MSB is multiplied by greatest power of 2. Among these, the greatest power is 7. So we have done that step. Now next step is add all the products in the step 2 and the answer is the decimal number. So it will be 1 into 2 power 7 plus 0 into 2 power 6 plus 0 into 2 power 5 plus 1 into 2 power 4 plus 0 into 2 power 3, continue, and last would be plus 1 into 2 power 0. Now 0 into anything would be 0. So 0 into 2 power 6 is 0. But 1 into 2 power 7 is 128. Similarly, 2 power 5 also we will get as 0 because we have multiplied it with its digit, which is 0. The same I will continue, and 1 into 2 power 0. 2 power 0 is 1. So 1 into 1 is 1. And after adding all these numbers, I will get the answer as 145. So the decimal representation of this binary number is 145. Again, you can try out with these two numbers and see what you get. Next, we have the logic gates. So logic gates are more like a building block in any digital circuit. And as the name says, it will perform some logical operation and it will give an output based on the inputs. So input can either be 0 or it can be 1. 0 we consider it as low, 1 we consider it as high, and based on the gate and the logic operation it performs, it will give an output that is again 0 or 1 or high or low. We will get a clear understanding of the logic operation by studying the truth table, which defines the behavior of the logic gate. There are 7 logic gates which we will be learning now, and each logic gate has its own symbol so that we can easily understand when it is represented in a circuit. These are the logic gates, and among these, NAND and NOR are called as universal logic gates, which means any function, any Boolean function can be represented by these two gates. Hence, we call it as universal logic gates. Let us now start by learning about the NOT gate. NOT means negation or a complement. So what this gate does is, this is the symbol, and it will give a complement of the input. So suppose input is 0, then it will give output as 1. And if input is 1, then it will give output as 0. This takes single input. So we have two inputs. This is the truth table. We call this as the truth table, and this is the symbol. And this is how we represent. So if the input is A, then A bar is called as the complement. This is also called as an inverter. So this logic gate is used whenever we want to invert an input. That was a very simple logic gate. Next, we have the OR gate. OR is somewhere correlated to the addition operation. So hence, we have taken, if this is two inputs, then the output of OR would be A plus B. That is how we represent it. And this is the symbol of OR gate. So OR produces high if one or both of the inputs are high, which means if any one of the input has 1, then the output also would be 1. This is the truth table. Here, since we have taken two inputs, so there will be 4 different combinations. So in the first combination, both the inputs are low, hence the output is also low. Whereas in the next 3 combinations, one of the input is high, hence the output is also high. This is how we write it. Y equals A plus B. Symbol is typically depicted as a curved line with inputs on the left and outputs on the right. Next, we have the AND gate. This is again correlated to multiplication. So it will give high when both the inputs are high. So 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, but 1 into 1 is 1. So we can represent it as A dot B, that is the output. Again, on the left hand side, we have input, right hand side, we have outputs. This is 2 input AND gate. We can further design 3 input AND gates as well. For now, as a beginner, we will understand 2 input AND gate, and this is called as the truth table. So we just have to learn the symbol, and rest all would be available in the truth table itself. These are the inputs A and B. We can also equate A dot B to Y. So Y equals A dot B is the output. Next, we have the NOR gate. So NOR is OR plus NOT. When I add an NOT gate after an OR gate, I will get the NOR gate, which means whatever the output we get in OR gate, complement of that output is the output of our NOR gate. This is the symbol of NOR gate. This is the OR gate, and since there is a bubble here, it becomes a NOR gate. And this bar indicates it as complement. We can define the truth table of the NOR gate like this. Output is high only when all of its inputs are low, otherwise the output is low. So in this truth table, you can see that in the first combination, both the inputs are 0. Only in that case, the output is 1. This 1 is complement of the output which we have in OR gate, this case. So a complement of this A plus B is 1, which is the output of NOR gate. Similarly, in these cases, since at least one of the input is 1, the output is 0. So this was about the NOR gate. Similarly, we also have the NAND gate, which means it is an AND gate followed by a NOT gate. And if we simply remember the truth table of the AND gate, then we can easily write the output of NAND gate as well, just by inverting the output we have in AND gate. Here, if we are defining this truth table, instead of looking for the cases where the output is high, we can directly define only one case where the output is low. The output of the NAND gate is low when all of its inputs are high. Otherwise, the output of the NAND gate is high. We have two slightly different or special gates, that is the XOR gate and the XNOR gate. This is the symbol of XOR gate, and this is how we represent the output. X stands for exclusive. So this gate is exclusive OR gate, which means its output is high only when the odd number of inputs are high, which means in this case there are only 2 inputs. So for 2 combinations, we get output as 1, because in both these cases, only one of the input is high and other all inputs are low. Suppose we have a 3 input XOR gate. In that case, the output would be high when in the input combinations, any one pin is high or 3 pins are high. Like that, we define the XOR gate. This is also addition, but it has an exclusive condition. Hence the name XOR gate. These are all the applications: parity checking, binary addition, and data transmission. It is more like an advanced version in digital electronics. For now, we just have to understand the XOR gate. Similarly, we have the XNOR gate, or a complement of XOR gate. So this is the XOR gate followed by a bubble gives us the XNOR gate, and this bar indicates it as a complement. So in this truth table, the output is high only when both the inputs or all of its inputs are same. That is, either it has to be low or it needs to be high. This is one way of defining. Another way of defining can be the output of an XOR gate is high when even number of inputs are high. So in this first case, Zero number of inputs are high, which means the output is 1. And in the last case, two number of inputs are high, which means the output is also high. And the second and third case, the output is low. So this is how we define a XNOR gate. Let us now understand the basics of a digital circuit. So a digital circuit is an electronic circuit that operates using digital signals. Now digital signals have only two values, either 0 or 1, that is low or high. While analog signals are continuous, digital signals are discrete. We have used resistors, capacitors in the previous videos when we studied about analog electronics. But in digital electronics, the components mostly comprise of logic gates, flip-flops, registers, and microcontrollers. Currently, we have understood logic gates, and all these things are more like an advanced version. So since it is digital signals, we represent the data using 0 and 1. And these circuits are designed such that it uses some logic operations like and, or, not. This, in other terms, we also call it as Boolean algebra. Applications are enormous. Some of that which we use in our daily lives are laptops, computers, smartphones, and many other digital devices. If you have tried out those two conversions that I had shown in the previous slide, you can cross-check your answers with this. That comes to an end of this video and also end of a series. So in the next video, we will design a basic electronic circuit. And today we have understood the binary system, how we can convert binary to decimal and vice versa. We have understood the basics of digital electronics, and we have learned about the 7 different logic gates, how we can remember them, their truth table and the symbols. See you in the next video. Thank you.